Welcome back to GCSE Minecraft and Chill. I hope you're having a cozy and relaxed day. Today's physics revision topic, we are going to start at the beginning, just like today's maths video, and talk all about energy, the fundamental physics topic. And we're going to go over the core concepts, why I find this topic interesting, and how you can use the bigger picture to improve your approach to exam questions. So grab a drink, get your revision notes, or whatever you're going to do while I entertain myself and maybe you with some Minecraft. I'm going to be continuing in this gorgeous tiger. I think I'm going to finish my roof and go from there. So if you know what I'm building and recognise the general structure, do comment below. I'll be very impressed because I've only just gotten started. Anyway, let's talk about energy. When I'm teaching this topic, I like to ask my students what they think energy is before we've even said anything. And it's so interesting to hear what people say and how different people conceptualize energy. It seems to always be this ethereal, intangible, undefinable thing. We just know that it is, but actually putting it into words can be quite tricky. And a good science student might answer me with an equation. Of course, we know that energy is defined in physics as work done if we're talking about forces measured in joules, but we also know that there's equations for energy depending on the situation that we're talking about. It could be power multiplied by time, or it could be proportional to some change, whether that's temperature or speed, or speed squared for kinetic energy, and so on. And if you're really familiar with physics, you might even be thinking you want to quote the famous equation proposed by the Einsteins, that E equals mc squared, which of course relates the amount of energy to something's mass using the speed of light squared. But even though these equations do tell us something, an incredible amount about the nature of the relationship between two quantities, it doesn't tell us anything about the nature of these things themselves. Like you can calculate the speed of something moving. That doesn't tell you what that thing is, right? So when you're learning about energy properly for the first time at GCSE, it's kind of just taken for granted that you know what energy is and you just jump straight into the equations. And intuitively, of course, we understand what energy is. It's kind of like what I was saying in the maths video about the concept of number. We do have an inherent human understanding of what these concepts are because we grow up with them. We know how they work because we interact with them. But defining or explaining and our logic and our reasoning and our working out in a tangible way is what leads to us realizing that actually there are some aspects of this that are otherwise obvious that we don't quite understand or we're not quite sure about. So how I then answer my students is, well, I tend to say that energy is most often measured or observed in terms of vibrations. That's all the temperature is. It's connected to motion inherently because of this, because it's vibrations. And you may have also heard that energy cannot be created or destroyed, only transferred. And that inherently gives us some kind of some motion, some direction of travel. So in this topic, in the Physics GCSE course, the focus is on learning about different kinds of energy transfer and, of course, the equations that accompany those transfers, because energy can be transferred from one kind into another, whether that's kinetic to gravitational potential, elastic into sound, or heat into chemical, or any of the others. And actually, one of my shorts this week, I went over all the different kinds that you need to know for that, so check that out if you missed it. I will link it below. But otherwise, we can measure energy in terms of it being locked up in a store, in a form of energy storage, like storing electrical energy in a battery, or thermal energy in an internal energy store. So we know that that's there, but that still doesn't really tell us what it is. So we can't really visualize it, it can't really be seen. So we have equations that describe the transfer, and we can measure how much energy is in something, is stored in something, but we can't see it. It just kind of naturally is intangible. So we use other concepts to visualize it. You might have already been visualizing energy as some kind of movement, or light, or sound, or some kind of vibration. And those are evidences of energy transfer from one storage system to another. So we can't see it, but we can kind of see the effects of it. And that kind of gives it this nature of being this kind of universal glue that holds everything together or pushes things apart. It allows something to happen. And that's where the description or definition of it being work done comes from. That's where that equation comes from. It's kind of the released potential that allows some kind of action to be performed or done. And if you continue to study physics into A level or beyond, you'll learn more about the nature of energy systems and models that we use to describe it, and understand it more deeply, and learn more about the universe, like in particle physics, or learning about things like dark energy or string theory, which are very cool. But for now, I think the best way to define and understand or describe energy quite simply, in order to understand it as best as possible, is vibrations, the frequencies that underlie everything to do with matter. Where there is matter, there's going to be vibration. At least that is until you get down to 0 degrees Kelvin, which is defined as an absolute zero, specifically because that's the temperature where an atom cannot vibrate or oscillate. Because all atoms, of course, which we envision as spheres with orbits of electrons whizzing around them, are vibrating, they're oscillating in place. That's how chemical bonds form, by these vibrations becoming intertwined and inherently interlocked with one another. That's how we sense temperature, when all the molecules in the air around us or in our skin start to vibrate more and faster. We feel that as heat. And if you heat something up enough, you provide the molecules with enough energy to break those intertwined, interlocked chemical bonds, things will degrade and fall apart. And I'm just trying to catch this fox. And so what I'm talking about here is something catching fire and combusting. That's just one particular form of chemical bonds breaking down that happens to involve a chemical reaction with atmospheric oxygen. But this kind of reaction, this kind of using heat to break a chemical bond, is an intuitive understanding of energy. It's an intuitive way that we want to describe energy, as heat or vibration, like fire. We think fire when we think of energy. And that's kind of also why New Age spiritual folks or the astrology girlies will describe fire signs as particularly energetic, because there's this natural relationship between energy and heat, and why they will also talk about frequencies, natural frequencies and vibes of things, of sounds and of the universe, because everything is vibrating or oscillating at some kind of frequency. Even the vacuum of space has lingering background radiation from the Big Bang, which is just energy being transferred via waves, and that has a particular frequency, and it's been measured. So everything has a natural frequency, and it's kind of interesting to explore and measure those. But anyway, I digress, as usual. So we're using, what I was doing is giving examples of the different times and places that we use the language of energy colloquially to describe or what we think energy is, or where we tend to interact with energy. And we even do that colloquially with ourselves to describe our own emotional, mental, or physical energy reserves, to refer to the amount of effort that we have done or are able to put into something. We talk about the energy when we walk into a room, or the energy of a crowd when it's being raised at a music gig, or when energy has been created and stirred within you by a song that moved you. And so we do understand energy as this thing that has the potential to move us, either literally or metaphorically, to some kind of transferred outcome, some kind of resultant output, or again, back to the concept of work done. And it's why characters like the mutants in X-Men, who can manipulate energy, are among the absolute most powerful of the mutants, because being able to manipulate or control the very nature of matter and how it vibrates and stores energy gives absolutely incredible potential to do very powerful things. And again, for another example, earthquakes are a fantastic example of this. Shaking and vibrations in the earth caused by tension being released deep in the earth's crust has the potential to bring about the destruction of some of the most solid buildings that we have on Earth's surface. So all of those examples are to say that even though we can't easily, tangibly describe what energy is, talking about it as tangibly as possible with lots of different examples kind of gives you a better understanding of why physicists and why physics, it is the literal study of interactions of energy with matter. And that's why it focuses on this topic first as your foundation before you move on to anything else, and why we are so focused on the equations, the models, and the diagrams that might be a bit boring, because they tell us about the transfer of energy from one store to another, and that's really the best we've got in terms of observing why things happen in the universe, right? And it's a lot simpler to conceptualize those things and measure those things and observe them than to directly try to observe or conceptualize the nature of this mysterious universal driving force that exists all around us. And I don't mean that literally, just to be extra confusing. Energy is not a force. Forces arise due to imbalances that result in energy being transferred. So forces are the pushes and pulls that move the vibrations around and transform them from one form to another, and that's subtly different. We will talk about that more when I get to the forces topic, but keep that in mind, the difference between force and energy. Try not to conflate them or confuse them. Before you get to grips with forces, you kind of have to become fluent in the language of energy transfers. And that's kind of why, because it is quite easy to get confused with what we're talking about, especially because we measure energy transfers and changes usually with forces, by observing forces and measuring them. They're a lot easier to measure. So that's why we look at things like heat capacity for thermal energy transfers, changes of state from solid, liquid to gases for the same reason, or kinetic and gravitational potential energy transfers, because it's easy to observe those, and all of the others as well, the chemical, the electrical, etc., as well as the efficiency of energy transfers from the frame of reference of having some kind of useful energy transfer versus some kind of wasted energy being transferred into forms that we didn't want it to be necessarily transferred into. And that's why next week I'll be talking about sort of energy part 2. I'll be talking about all the different kinds of energy and power generation that we use, renewable and non-renewable, and I might include some chatter about capitalism again too, inevitably. What's a video with of mine without calling out capitalism at least once. I do tend to do that. But for now, let's change tack a bit and sort of to build you this kind of bigger picture, to understand why you've got to learn all of these equations and diagrams to do with energy and energy transfers. We're going to focus on heat. And again, because like I said, that is the most tangible and easily recognized form of energy storage and energy transfer. We do have a very, very human understanding of heat and how it works. So it's a fantastic entry point for learning all of the concepts you need to understand about energy transfers, as well as forces for motion and waves and electricity and space and everything else that you need to learn in your physics course. So this is kind of why we start here, and why I think it's kind of interesting. Again, in the same way that I think number is interesting, you might think it's boring because it's kind of the easiest and it's the starting point, but it underpins everything. And if you really understand it, you're well on your way to kind of mastering the course, really. Anyway, I digressed again very quickly. It didn't take me long. So we're going to focus on heat. And as much as I personally would wish otherwise, we humans cannot bend fire. We are not firebenders, though I would love to be, if we were living in the world of Avatar: The Last Airbender. So because of our lack of ability to do that, for most of humanity's existence on this planet, one of our primary occupations in terms of having stable, safe shelter for survival has been controlling the temperature of our environment, especially because we are very picky creatures and we need to optimally exist in a very small temperature range. And especially for those of us that live in colder climes, heating our homes has been one of the biggest forms of energy usage up until electricity and vehicular transport as opposed to the old horse and carriage. Since that became a thing, kind of our energy use has shifted. But again, I'll talk about that next week. So back to heat. For early versions of humanity, heating up our living space kind of simply meant lighting a fire. And it was actually the opposite problem that was kind of the intellectual problem to solve. It was keeping cool. That was a problem that our ancestors in Africa figured out with incredible architectural designs and understanding of the materials around them, using principles of conduction, convection, and radiation, understanding how heat moves into and through their living spaces with the materials that they were using to create optimal living spaces in terms of the geometry of the building as well as the materials. Whereas in Britain, the focus post-industrial revolution anyway has been on close packing as many homes and structures as possible to accommodate a dense population in a relatively small landmass. So we have all of these horribly inefficient, poorly insulated, uncomfortably temperatured homes. No matter what the season is, it seems to always just be the wrong temperature. But anyway, so in a bog standard house, you might have a living room with a radiator in it, and that radiator might be powered with heated water, which will travel through bent pipes, circulating the heat through the metallic structure. So how does that heat going through the pipes in that metal heat up the room? How does that thermal energy transfer to our room? So to answer that, you have to understand how vibrations are going to travel through the three different states of matter at room temperatures and pressures, the solids, liquids, and gases energy transfers. So I already mentioned them. We've got conduction, which is passing energy through solids when neighboring atoms are figuratively bumping into one another, creating a literal wave of motion that bounces around within the solid. And all solids are doing this all the time. Some are just slower than others, and we call those poor conductors of heat. So think about if you've ever been inside a mosh pit or inside a really crowded gig and someone bumps into you and then you bump into the next person, and we get that before we get to the situation of a crowd surge or anything. I'm just talking about the small little bumps. Those are energy transfers happening, and that's exactly what's happening in solids. I say exactly, I mean metaphorically, figuratively, whatever. Anyway, whereas fluids like liquids and gases tend to transfer energy via convection and radiation. A diffusion gradient from hotter to cooler will make the heat energy trickle down the gradient from hot to cool. So physically, swirled patterns of motion are created where the heat will physically move from hotter regions down the gradient to cooler regions. And this happens in a cycle because of density changes, where things expand and get less dense when they're hotter and they become more dense when they cool down. Whereas radiation is a bit different. It can be conceptualized more like a laser beam transfer of energy in a given specific set of directions. So obviously in the case of a radiator, this is really useful, being able to convect and conduct and radiate heat. But for situations like lighting a room or driving a car or simply sending an electrical signal in your computer, heat tends to be the one thing that wastes energy, diverting it away from the purpose that we actually wanted it for. So if you ever asked in a question if some energy transfer is happening, what's the wasted energy? I want you to think automatically, is it heat? Because chances are it's probably heat. So I want that to be your go-to to think about. Because heat is pretty much inescapable if we're talking about energy transfers, because those pesky vibrations are going to transfer from atom to atom contact, hence the concept of friction. Again, think of people packed into a crowd, bumping into one another. And we might not necessarily want the heat. Again, unless we're heating a room or trying to heat something or cook something, generally we don't want heat energy involved. So it's usually a waste product of energy. Now, that concept naturally will lead us to conclude that we can quantify how much useful energy is being transferred from one store to another, or one situation to another. by using a percentage. So we're calculating energy efficiency now as a percentage by dividing the useful energy by the total energy that was input to the situation to get that useful energy output that we wanted, and then we multiply that fraction by 100 to get it into a percent. So the more you know about every single specific energy transfer that is happening and what vibrations are going to be leaking energy away from your intended use of energy, the more accurate your evaluation of your energetic process, of your efficiency, is going to be. And that's useful for all sorts of things. And again, that's something I will mention next week with power generation, for comparing different types of energy generation or power generation. So hopefully this has helped you conceptualize energy a little more clearly and given you a full picture for why we study the seemingly boring or useless things like the heat capacity of a fluid, or how much energy is stored in a spring, or what energy is transferred during a bungee jump or something. It's actually very useful, but that'll do for today. Thank you for watching if you made it this far, and if you enjoy these chatty revision videos, please give me a like or let me know in the comments what was useful about this for you, as I may conclude this series once I've gone through each of the major GCSE topics, but if people like it, I'll keep it going. Whatever you do, don't forget to be kind to yourself, as our words are our spells, and have a lovely rest of your week. I'll see you next time. Yalla, bye.